Let's take a look at how alpha and beta risk work out when we're dealing with a more discrete probabilistic function, not a continuous function like under the normal curve. So for this, I want to use an example from our Devore text. This is example 8.4 from pages 318 and 319 if you want to follow along. It's an example where we're looking at the likelihood that a car in a test crash won't be crumpled. So again, it's a binomial situation rather than a continuous situation because there's a set number of cars that will be tested and they either will or won't be damaged in the crash. So we can't use a normal or even a t-distribution for this. We have to use basically a binomial discrete distribution. So what we're given in the problem is a starting point that 25% of the cars tested will not fail. We're going to test 20 vehicles. That gives us an expected value of 5. So we expect 5 of the cars to be okay. And we're looking at a 0.1 alpha as we go through. So that's the level of accuracy we're looking for as an alpha risk of 0.1. So if we take that data and start to do a hypothesis test on it, the null hypothesis will be that the expected value of 5 is the true value, and we're interested to know if more cars than that come through the test. So the hypotheticals we pick up at this point will be increasing from our expected value of 5, so I'll just take 6 through 16 as a range of numbers. That's probably higher than I need because of the way the curve will work out. But we want to know what's the probability that we'll actually see that number coming through as we go through. So how many cars will come through without a visible damage, and we're hoping it'll be a larger number. We'd like to be able to prove that statistically as we go through. So if we take our hypotheticals, we can plug that in through a binomial distribution. The binomial is easy enough to work out. It's basically our B10 minus 1, so we're looking at 1 less than that because it is a binomial, equated over a range of 20 to give us probability of 0.25 and true. So we want the cumulative binomial probability of fewer than 6 coming through or fewer than 7 coming through, and that's the probability that we end up with coming through. So that's our binomial distribution. We look at the p-value of that is simply 1 minus that, the probability that we'll get that larger range of values. So again, that's why we took that B10 minus 1. We actually want the probability of 5 or fewer, so when we subtract it from 1, we get the actual 38% probability of having 6 or more. So that's just the way we calculate the binomial distribution. I've included an if statement there to compare that value to the alpha risk that we've taken, so I can indicate whether it's being rejected or not. And when we extrapolate that value over the range of values, we find that for 6, 7, or 8, we would not reject the null hypothesis because their p-values are lower than the 0.1 alpha risk that we're after, but all the values higher than that have a p-value of less than that, and so we would in fact reject the null hypothesis going through. If I treat that as my cutoff, so my cutoff was 8, at 8 or less I'm going to reject the null hypothesis, so my cutoff is really 9. I can use that cutoff of 9 to calculate the beta risk for a series of other probabilities. Again, the null hypothesis had a probability of 25%, so I want to know the probability that what if the real probability is higher than that, what's the likelihood that I will accept the null hypothesis if in fact it's false. So I can do the binomial probability of that coming off of my factors, and that gives me my rate of what the beta risk will be associated with that. So at a cutoff of 9, I have a beta risk of 0.887 if in fact the true value is 0.3, and the beta risk as usual will fall and decline as the numbers go up, simply because the farther this p-value gets from the expected value of 0.25, the lower the beta risk will be as I go. So again, beta risk decreases as the true value wanders farther and farther from the mean. I'm not sure why, but in the text, the authors suggested that we take this 0.102 and round it to 2 decimal places to come up with that number, making that 1.02 now reject the null hypothesis. It's statistically incorrect, but they do it in the text for some reason. That would change our cutoff from 9 down to 8, because now we're going to reject on 8. So when I plug 8 in here, that's when these numbers right here match the table in the book. So if you're comparing the numbers in the book to what I did here in the problem, it's because they've taken that 0.102 and changed it to 0.10 on the top of page 319 that causes that to happen. But if I don't leave that in. If I leave it at the 0.102, I won't reject at that point, in which case I would use a cutoff of 9, and I'm going to get slightly different answers here than you would have had in the text. But it's up to you how accurately you want to do the calculations as you go through. So beta decreases as I see my way down. The farther I get from my mean, the lower my beta risk is as I go. So for instance, here's a graph of some of this data associated with that image of 9. You can see the beta risk associated with 9, which is a 0.3. At 0.3, I have a significant beta risk of 88%. As I go to 35%, it falls to 76.2. But if I were to presume a different cutoff, so use that cutoff of 8 that I had when I changed the 102 to 1, the beta risk lowers significantly. Again, the closer I get my cutoff to my original value, my beta risk profile changes as I go. So as my cutoff increases, I see a larger and larger beta risk seeing my way through. So if the true cutoff were way up by 10 or 11, I'd have a 98% chance of having that risk. You can play with that as you go through. But what I'm interested in primarily is what is the change, what is the critical value, what is my cutoff in terms of the level at which I start rejecting the null hypothesis, and for that cutoff value, what does that do to my beta risk given the real number coming through. That's your alpha beta risk for a discrete population.